Hey guys, welcome to this video on level 2 algebraic procedures. Going to be looking at logs in this video. Okay, so I created this PowerPoint. Okay, so algebraic methods, logs by me. So the first thing we're going to look into is being able to simplify logs. Okay, so basically a few simple rules we're going to remember when simplifying the logs. One is when you minus a log with another log, assuming that really important, I forgot to put this in the slide, but very important thing is when I say a log minus another log, I assume that the base is the same, okay? So for example, a base 10 log minus a base 2 log, okay? So basically the base has to be the same in order for this to work. If the base isn't the same, then you cannot apply this rule. On your calculator, it's default on log 10, okay? It's, the base is just default at log 10, so basically the thing to remember, if it's the same base, if you minus a log, you actually divide, okay? So for example, if you have log A minus log B, you get log of A divided by B. So for example, if I have log 10 minus log 5, that will give me log 2. Next thing to remember, when you add the logs, you actually multiply. So once again, this only applies if the base is the same, okay? So for example, if I had log A plus log B, then the result would be log A times of B. And finally, one last important thing to remember is be careful when there's a coefficient. So when I say coefficient, it's basically a number in front of the log, okay? So for example, we have 3 log A, okay? So when I say 3 log A, that is not equal to when I say 3 log of A, that is not equal to log 3A, okay? You cannot multiply the A by 3. Instead, you can rewrite 3 log A as 3 log A can be rewritten as log A plus log A plus log A. For example, you have 3 times 2. So 3 times 2 is the same as saying just 2 3's. So basically, you just say 3 plus of 3. It's the exact same logic here. So 3 log of A is just log A plus log A plus log A. But if you come back to rule number 2, is when you add logs, you actually multiply. And when therefore, log A plus log A plus log A, that's actually multiplying them together. So therefore, we're actually going to get our answer as 3 log of A is actually log A cubed, okay? So that's a really important point to remember there. Alright, so next slide, we're going to be covering some simple examples of the logs. So just some basic questions, including the plus and minus of logs. So question number 1, what is log 2 plus of log 3? So we're going to go back to our addition rules. Our addition rule states that adding logs is multiply, so our answer will come to be log 6. Number 2, we have log 16 minus log 4. We're going to go back to our minus rules, okay? So when you minus 2 logs, it's divide, so our answer is going to come out to be log 4. Question number 3, we have log 64 minus log 8 plus log 2. So doing these types of questions, you just just do it in the way you would normally do a question, okay? So you just, in a normal way you would do addition problems. So in addition problems, for example, you have 2 plus 3 plus 2. So you do 2 plus 3 to give you 5, then you do 5 plus 2 to give you 7. Same thing here. So log 64, we're going to do log 64 minus log 8 first. That's going to give us log 8. And log 8 plus of log 2, that will give us the log 16. Number 4, 4 log of 2 minus log of 2. So remember when I said the coefficient rule? That's 4 log 2 is the same as saying log 2 to the power 4. 2 to the power 4 is 16, so we can rewrite 4 log of 2 as log 16. Log 16 minus log 2 is actually log of 8. And number 5, we have 3 log 3 minus 2 log of 3. So we can rewrite 3 log of 3, 3 to the power 3 is 27. So we can rewrite 3 log 3 as log 27. And we can rewrite 2 log 3 as log 9. Log 27 minus log 9 is actually log 3. Alright, some basic examples there. We're going to be moving on to the log rule of the base power outcome rule, okay? So I like to call this the BOP rule, okay, the BOP, so base power outcome. So basically, what I'm saying here is you should see that log base of B outcome equals to the power, okay? So if you read it from left to right, you should get BOP. So that's why I call it the BOP rule, okay? So log base B to the power of P equals to the outcome. So, so where B to the power of P equals to O. So base to the power is equal to our outcome. some examples using the BOP rule. So, alright, so we have log base 2, 16 equals to x. So, okay, so remember our BOP rule, we have to rewrite this as, we have to rewrite this in a different way, okay? So we can say the base to the power of x equals to 16. So 2 to the power of x equals to 16. And we should be able to see here very clearly that x equals to 4. Sorry. Number 2. Log x 64 equals to 2. So in this case, we apply the exact same formatting rules. So base of x to the power of 2 equals to 64. So x squared equals to 64. And your answer should come out to be 8, okay? Number 3, so log base 3 of x equals to 3. So in this case, we can just rearrange once again. So 3 to the power of 3 equals to x. And therefore, we should be getting our x value as 27. Number 4, log base 2 of 1024 is equal to x. So we can rewrite this as 2 to the power of x equals to 1024. And therefore, we can solve x as 10. So x should be equal to 10. So once again, some simple questions involving the BOP rule, okay, the BOP rule. You'll see these types of exam questions in the level 2 exam every year, okay, guaranteed, okay. Every year there are some log questions in this format as well, achieve points there, okay. So some easy achieve questions you can get. So rearranging log of, okay, but when I say rearranging log, I mean the log on both sides, okay. So what I'm trying to say is, to rearrange log on both sides, we need to have the equation in the form of base to the power equals to outcome. Okay, so if we rearrange this, okay, we're going to take the power down, and we're going to log on the right hand side as well. So basically, we take the power down, we log the base, and that's equal to the log of the outcome, okay? So basically, if you see here, we take the power down, so the power is no longer a power, it's a coefficient. So the coefficient times of the log of the base is equal to log of the outcome, okay? So P log B equals to log O, okay? And basically, those are the steps. Take the power down as a coefficient, and log base and log the outcome. So that's when we say log of both sides. Therefore, we can say log base B of O equals to P. So that goes to base to the power equals to O, and therefore we can rewrite this as P log B equals to log O. And we can go the opposite way as well. Okay, so we can go from form A to form log base O equals to P. We can go from that to base to power equals to outcome, and we could go to P log B equals to log O, and we could go vice versa. So it's both ways. Alright, so we have a few practice questions in rewriting log both sides form. So question 1, log base 2 of 24 equals to x. 2 to the power of x equals to 24. So right now you can see it's not really easy to solve this question right now. You need to take the log of both sides and then solve manually, okay? So we can say x log of 2 equals to log of 24. And now we can just use our basic rearranging skills in algebra. So we can say log 24 divided by log 2 equals to x. And that should give us x equals to 4.58 as our answer. Question 2, log of base 6 equals to, so basically in these questions, I want to show you what you should log on both sides and what you shouldn't log on both sides. So as you can see in this question, there is no need to log on both sides because you can simply type in 6 to the power of 3.4 on your calculator to find your x value, okay? So your x value should, x value should come out to be 442.3. So in case number 2, there is no need to log of both sides. Let's look at case number 3. So case number 3, you have log of x, log base x equals, 1000 equals to 3.4. So x to the power of 3.4 equals to 1000. Alright, so for this question, okay, this one as well, you do not need to log on both sides. The reason we don't need to log on both sides is because we can simply type in on our calculator 1000 to the 3.4th root, okay? That's what we do. So on your calculator, it should be our root X button, so 3.4 root X, root of 3.4 to 1000, and you should get your X value. If we did log this, for example, we can say 3.4 log of X equals to log of 1000. However, we're left with log X, and log X is a lot harder to solve for. So the easy way to do this is just to the 3.4th root. So in this case, we don't have to log on both sides. So basically, your answer should come out to be 7.63. It's basically the only time you actually need to log on both sides is if you have a number to the power of X equals to another number. That's the only time you need to take log on both sides. So now I'm going to look into some practical use of logs. So in exam questions, equations are usually given or require you to write a formula in the form of, so y equals to a times r to the power of t. Okay, so when I say y is our outcome and depends on the context. For example, I can say this person has been saving up her money and he starts with this much money and the money increases by this much per year, for example. Our y in this context is the amount of dollars he has after a certain amount of time. So if I have a certain amount of time, after a certain amount of time, this person will have a certain amount of money. And that is our outcome. That's our y value. Our a value is the original number at the start. So basically, we can say that this person has $1,000 in the bank, and this money increases by, for example, 10% every year. Our a value would be the 1,000 because that's how much the person starts with at the start. So when t equals to 0, the person has $1,000 in the bank. Our r is the rate of increase and decrease. So coming back to our example, I can say this person has $1,000 and it increases by a rate of 0.1 per year. So our rate of increase or decrease is just basically how is the money changing over time. And of course, lastly, our t is just the time. So basically, time can be any unit depending on the question. For example, if I'm doing a banking question, I could say t is in years. But for example, if I'm saying like bacterial growth question, like how fast bacteria is growing, I could say that in terms of minutes. So basically, you have to read the question in terms of how time is measured. It's different every time. It's just depending on the context, like our y value. Application type questions of log. So most questions involve a percentage or decimal increase or decrease over a period of time t. So I'm saying most questions do this, but not all questions, okay? So when I say most, I think I could confidently say about 90% of the questions you'll come across will say something changing with respect with time, okay? So for example, I have an example here. Dave has $250 and the amount of money he has increases by 10% each week. So we can rewrite the equation as I just wrote m as money, so money equals to original amount of money. So originally Dave had $250 and multiplied by 1.1 to the power of t. The reason it's 1.1, okay, so it's really important that you understand this, because the question says it increases by 10% each week. So when I say increases, that's 1, that's the whole thing, plus of 10% on top of that, okay? So that's 1 plus of 0.1, because 10% is the same as 0.1. So we can say 1 plus of 0.1 is our rate. So that's how we get the 1.1, and it's to the power of t. Yeah, I've written here. So m is the amount of money that Dave has. $250 is what he had originally, and t is the time in weeks. Okay, so basically, remember some important things here. So when something is referred to as an increase by X amount, the increase is 1 plus of X, like I just said. So if it's increasing by 10%, it's 1 plus on top of whatever it's increasing by. So same thing for referring to decreasing. When I say decreasing, we can say it's 1 minus the decrease. So we have the whole thing and it's decreasing by this much. And just one more bullet point, sorry about it so far down, but remember to convert percentages to decimals, okay? So for example, if we have 40%, that's the same as 0.4, or if we have 0.4, that's the same as 40%. Alright, some common exam questions that come in the exams every year. So I have an example here. So Jake is growing fungi. Imagine, assuming Jake starts with 2 organisms, and the amount of organisms increased by 150% per minute. Find how long it would take for there to be 1,000 organisms. Okay, so first thing we've got to do is model our equation, okay? So our equation is model your variables. So our A is the initial amount of organisms. In this case, it's 2. We start off with 2. The rate of increase is increasing by 150% per minute. So basically, like I said before, it's the whole thing plus of whatever we're increasing by. So basically, we have our 1 plus of our 1.5, which is 2.5 is our rate of increase. Our time is our time in minutes, we're trying to find that. And our population size of fungi we're trying to find is 1,000, okay? So we can just rewrite this into our equation. So setting up the equation is step 2. So 1,000 equals to 2 times of 2.5 to the power of t. We can simplify this equation by moving the 2 to the other side. So 2 times that, now it's 1,000 divided by 2. So 500 equals to 2.5 to the power of t. Okay, so now remember, if we're going back to a few slides before, now we have an outcome, and we have an outcome, we have a base to the power of an unknown. So now we need to use our log rules, okay? We need to take the log of both sides, okay, and we can solve for our t. So take log of both sides. So we can say log of 500 equals to take the power down and then log of the base, so t log 2.5. So therefore t actually equals to log of 500 divided by log of 2.5, and that should give you your answer as 6.78 minutes. The reason that's minutes is because it increases by this much per minute, okay? So that's important to keep in mind, the unit at the end. So you have to going back and reading the question, very important. Alright, so another example here. Jake now releases a toxic chemical on the fungi population of 1,000, and the population begins to die at 15% per minute. Calculate the time needed for the population to reduce to 100. So in this question, it's exactly the same as the last question, except this time we're not dealing with an increase, we're dealing with a decrease. So we just need to reverse everything, okay? So once again, step 1, model our equation. So A is the original amount of fungi we have. Okay, you guys might be confused, why is it not 2? The reason it's not 2 is because now, when he releases the toxic chemical on the population, there was 1,000. Okay, and we were trying to measure how long it would take for the toxic chemical to kill until 100. So basically, the starting amount of population is actually 1,000 in this case. Alright, so looking at R, our rate of decrease is just 1 minus of our percentage or our decimal, which is 0.15, and our rate is 0.85. Our population is 100, okay? So once again, it's the exact same thing. We model the equation, so set up the equation, so 100 equals to 1,000 times of 0.85t. So in this case, we're doing the exact same thing. We're moving the 1,000 to the other side. So therefore, 0.1 equals to 0.85 to the power of t. And just fast forward a little bit, we just take the log of both sides. And therefore, we should find that our t should be coming out to be 14.17 minutes as our answer. Alright, so this is a past paper example. Okay, so past paper example here. A computer depreciates continuously in value from $4,699 to $1,500 over a period of 4.25 years. The value, y dollars of the computer, t years after its value was $4,699 can be modeled by a function of the form y equals to a r to the power of t, where r is a constant. Find the computer's value after 6 years. Alright, so once again, step 1, identify the values. We have our initial price, which is our starting value was $4,699. It depreciates, so it decreases to $1,500, and we also have the time it takes. So this time we're trying to find our R value, okay? So we have our time it takes is 4.25 years. Number 2, setting up the equation. 1,500 is equal to the initial amount times of the rate to the power of time. So therefore, if we simplify this, we move the 4,699 to the other side. We should get that, rearrange and solve for R. So 1,500 divided by 4,699. And because it's R to the power of 4.25, we just need to do everything to the root of 4.25. And that will give us our R value. And you should find that R should give you 0.764 as your answer. Alright, we're not quite done yet. So to answer the question, we need to find the computer's value after 6 years. So we're going to substitute our rate back into our equation and find what is the price of the computer after at t equals to 6. So our same variables, except now we know the rate. So therefore, if we substitute these numbers in, we should get our price to be $934.47. Alright, so next part of this we're going to be covering is substitution. So this is substituting a specific term for just substituting a specific term for x and solving quadratically. So basically, if we bring sometimes a log may be too difficult to solve manually, and we need to substitute an expression as x and solve not as, that should be and, sorry. So and solve quadratically first. So for example, this is an example. So example, we have a 3 bracket log base 2x to the power of 2 plus 6 log base 2x plus 4 equals to 0. So looking at this, you might be thinking, what the heck is this? This is really hard to solve. And I agree with you, this is pretty difficult to solve. So it is possible to solve, but like I said, it was pretty hard. So in this case, we can use the substitution, okay? So we can substitute a specific term as x temporarily, okay? We can use substitution and substitute an expression as x. So in this case, we can looking at here, we can see, oh, it's something to the power of 2. And there's something, it's just that, but with no power. So you can be thinking of, we can substitute log base 2 of x as x. So therefore it becomes, therefore we can say log base 2 of x equals to x and solve as a quadratic first. And this will just become 3x squared plus 6x plus 4 equals to 0. And that's how you would model an equation for substitution. Moving to a few other questions, a few examples here. Oh, sorry guys, that 0 shouldn't be there. I kind of messed that up. Sorry. So one is 5 log base 8x squared to the power of 2 plus 2 log base 8x squared plus 8 equals to 0. So in this equation, we can just substitute log base 8x squared as x, and we can rewrite this as a quadratic equation. So we can say let log base 8x squared be x. So in the exam, it's crucial that you write this statement. If you do not write the statement, then the marker does not know what you're making as x, and therefore you won't get the deserved marks. So if we let that be x, and just becomes 5x squared plus 2x plus 8 equals to 0. Take another example, okay? So I've gone a bit extreme with this just to let you understand, okay? This is a bit extreme. NZQA won't normally give you this, but I'm just trying to make a point, okay? So 2 of this squared plus 6 of this plus 9 equals to 0. So we can say that 6 of that, so this log base 8x squared plus 6x plus 5, we can substitute that as x. And therefore our quadratic will just be 2x squared plus 6x plus 9 equals to 0. And that's just really simple examples, okay? So our next steps is actually beginning to solve the equation, okay? So we're not just modeling the equation, we need to start to finding out how to solve, okay? So next steps is, after rearranging in terms of a quadratic equation, we need to substitute both values back in terms of the expression we substituted x at and solve. So that statement might be a bit confusing. That statement might be a bit confusing. Okay, I'm gonna use a practical example. So consider this. So log base 2x to the power of 2 plus 5 log base 2x plus 6 equals to 0. So okay, we're gonna make we can make log base 2x be x, and we can rewrite our equation as x squared plus 5x plus 6 equals to 0. Now, so quadratic is really easy to solve. So we just solve for x in this situation. So we can find that x equals to 3 or x equals to 2. Okay, really key thing here is we can't stop here, okay? It's because we need to substitute 3 and 2 back into the term we substitute as x. So we let log base 2x be x. So we need to substitute that back. So we need to substitute back, okay? So basically we can say 3 equals to log base 2x, or 2 equals to log base 2x. And now once again, it's just using the really simple BOP rule here, okay? So base outcome power rule here, and we can solve for our x values. So x equals to 2 to the power of 3, or x equals to 2 to the power of 2. And therefore, you should get your answer as x equals to 8 or x equals to 4. So really simple examples there. And this is always an excellence level question. So just by doing these few steps, you'll be able to guarantee yourself an excellence mark, okay, for that question. Now here's a past exam example. So you have solved the equation log base 8x to the power of 2 plus 2 log base 8x minus 4 equals to 0. Okay, once again, we're going to use our substitution. So step 1, identify the variable to substitute x as. In this case, it's log base 8x. So now we can rewrite your equation as a quadratic. So 6x squared plus 2x minus 4 equals to 0. If we solve this, we can see that x equals to -1 or x equals to 2 over 3. We're not quite done yet. We need to substitute these values back into the original thing we substituted as x. So log base 8x, okay, so going too far ahead, sorry. So step 3, you substitute back, okay, that shouldn't say black, it's just substitute back and solve for x in the logs, rearranging using log rules if necessary. So we can say -1 equals to log base 8x, or 2 over 3 equals to log base 8x. So therefore we can say, using our BOP rules, once again, if you forgot what that means, just wind back in the video, okay? So 8 to the power of -1 equals to x, or 8 to the power of 2 over 3 equals to x. And we should be able to solve for x. Our x value is either 1 over 8 or x equals to 4. And this is an excellent level question, okay? So just by doing these few steps, you'll be able to get a guaranteed E7 for this question. So it's essential you need to know how to do the steps of this question. A few excellent examples. Okay, so that's our substitution part done. So now I'm just going to look at a few excellent examples in past year papers. So it says D, rearrange the formula a to the power of x equals to 5 to the power of x minus 1 to make x the subject. Okay, so in this question, okay, we need to, first thing we got to do is we need to take the logs of both sides, because we have a to the power of something and we have 5 to the power of something. We don't like that, okay? We want x at the bottom, so we take logs of both sides. So we can say x log a equals to x minus 1 log 5. Basically, that's just our log rule, okay? Log of both sides rule. Number 2, we're going to expand, why am I saying, it's not the left side, it's the right side of the equation. Sorry guys, I made quite a lot of mistakes in this PowerPoint. Sorry about that. So it should say expand the right side of the equation, okay? So therefore, x log of a equals to, just basically expanding like you normally would in algebra. So x log 5 minus log of 5. And now we can move the x log 5 to the other side. Move x log 5 to the other side, so it becomes x log a minus x log 5 equals to negative log 5. And notice now we have a common coefficient. And if we have a common coefficient, we can just take it out. Common factor, sorry, not necessarily coefficient, but now we have a common factor of x. We can take that x out. So we can take the x out of the equation, so we can move it outside the brackets, and we can say x times of log a minus log 5 equals to negative log 5. And see, you have x by itself now. And once you have x when you have x by itself, you can just move the other thing to the other side and divide. So it's x times of that, so on the other side it will be divided by that. So number 5 will be rearranged for x. So therefore x equals to negative log 5 divided by log a minus log 5. And once again, this is an excellent level question, okay? You can guarantee yourself an excellent E7 for this section of algebra if you can guarantee yourself to be able to do these types of questions. So I'm going to be looking through one final example. So it's really similar to the last example, but I want to make sure that you guys know how to do these questions, okay? So make x the subject of this equation. Once again, we take the log of both sides. So our result is 2x log a equals to x plus 1 log b. Expand the right side of the equation, simplify by expanding and simplifying. So 2x log a equals to x log b plus log b. Basically just how you would normally do algebra. I don't really know how to explain that any easier. So 3 you would factorize, okay? So basically, okay, so I've skipped a step here technically. So you have to move the x log b to the other side, okay? So once you move the x log b to the other side, you have a common factor of x. And once you have a common factor of x, that's good news. And that means we can factorize, so x times of 2 log a minus log b equals to log b. And once you have x by itself, you can just move it to the other side. So make in terms of x, so therefore, log of b divided by 2 log a minus log b equals to x. Where's my equals to x? Okay, just add an equals to x there. Sorry about that. So that's it for this slideshow, okay? I hope you enjoyed. I hope you learned something from this slideshow, okay? If you did, please drop a like down below. And thanks for watching this video and stay tuned for the next one. Thank you. Bye.